All right, so today we're going to solve October-November 2021 paper 41. All right, here we have question number 1. Question number 1 says, when dilute sulfuric acid is electrolyzed, water is split into hydrogen and oxygen. So here they've shown the equation for the electrolysis of water, right? Water is broken down into its constituent elements, hydrogen and oxygen gas. A current of X amperes is passed through the solution for 14 minutes. Okay, so we have a current of X amperes. We don't know what current we're passing, but we're passing it for 14 minutes. And we see that 462 centimeters of hydrogen gas are produced at the cathode. Remember, at the cathode, what we have is we have reduction taking place. So hydrogen is reduced at the cathode. And obviously here, since we're producing 2 hydrogens, I'm going to write it over here. Right, this is the half equation for the cathode. Reduction is taking place, or gain of electrons are taking place at the cathode. And this 462 centimeter cube of hydrogen gas are measured under room conditions. Calculate the number of hydrogen molecules produced during the electrolysis. So we know that the volume of any gas is simply the number of moles times 24,000 centimeter cube. Right? Since over here we have the volume in centimeter cube, we know that 1 mole of any gas occupies 24,000 cm cube under room conditions. Now we already have the volume given to us. We have 462 centimeter cube. And this is equal to the number of moles times 24,000, giving us how many moles of hydrogen gas? So we know that the number of moles over here comes out to 0.01925 moles, right? Now they want to know the number of hydrogen molecules. So if you guys remember, the number of molecules is simply the number of moles times Avogadro's number. That's 6.02 times 10 to the power of 23. Another way of thinking about this is we know that 1 mole of hydrogen gas will have 6.02 times 10 to the power of 23 molecules. So then 0.01925 moles mein kitni molecules hongi? That's what we want to figure out here. So then we can say that the number of molecules here is equal to, so again, the number of molecules here is simply 0.01925 times 6.02 times 10 to the power of 23, giving us 1.16 times 10 to the power of 22 molecules. Part B of the question says, calculate the total number of electrons transferred to produce this number of hydrogen molecules. We've already written down the half equation over here for the formation of hydrogen gas at the cathode. And what we can see is that for every 2 moles of hydrogen gas, we have 4 moles of electrons. For every 2 moles of hydrogen gas, right, we have 4 moles of electrons. So if I have 1.16 times 10 to the power of 22 molecules of hydrogen gas, how many electrons do I have? We'll have twice as many, right? If you just cross multiply here, we know that for every 1 molecule of hydrogen, we have 2 electrons. For every 1 molecule of hydrogen, we have 2 electrons. For every 2 molecules, we have 4. So there's going to be number of electrons will be twice the number of molecules of hydrogen. So we can see over here that the number of electrons that we have is 2.32 times 10 to the power of 22. That's the total number of electrons. Calculate the quantity of charge in coulombs of the total number of electrons calculated in part B. Now, if you guys remember, what is the charge on 1 electron? The charge on 1 electron is 1.6 times 10 to the power of negative 19 coulombs. So if I have 2.32 times 10 to the power of 22 electrons, what is the charge? And we can say that the charge over here, let's call that Q, right, is equal to the total number of electrons, that's 2.32 times 10 to the power of 22 times 1.6 times 10 to the power of negative 19. And this comes out to 3.71 times 10 to the power of 3, or you can just say 3710 coulombs. Okay. All right. Calculate the current X passed during this experiment. Now, to calculate the current X passed through this experiment, we already know the charge that was passed in this experiment. We want to find the current. We want to find the current over here. And we know the time that we took the experiment for. The time over here was given to us in the question as 14 minutes. And the charge that we had was 3710 coulombs. So we have 3710 is equal to the current, that's X, times T. And T over here, obviously we're going to take in seconds, so that's 14 times 60. Okay. And if we do the math, what do we get X as? So here, the current comes out to 4.42 amperes. Again, make sure the charge is taken in coulombs and time is taken in seconds. So the current is 4.42 amperes. All right. Part E of the question says, the standard entropies of the three species are given in the table. Calculate the standard entropy change for the reaction 2H2O forming two hydrogen plus oxygen gas. In other words, calculate the entropy change or the standard entropy change for the electrolysis of water. We know that the standard entropy change for a reaction is equal to the standard entropy of all the products, right, minus the standard entropies of all the reactants. All right, now over here, the products that we have are, we have 2 moles of hydrogen. So the standard entropy of the products will be 2 times plus 131 for hydrogen, plus we have 1 mole of oxygen, so that will be 205. And then we're going to subtract the standard entropy of the reactants, and we have 2 moles of water here, so that will be minus 2 times 70. Over here, this calculates out to positive 327 joules per Kelvin per mole. Whenever you're writing a value for entropy change or enthalpy change, always include the sign. Okay, so don't say 327, say positive 327. Okay, and again, we have a positive entropy change, and we could have predicted that just by looking at the, we know for a fact that we'll have a positive entropy change because we have more moles of gas on the right hand side. So we've actually increased the entropy in this system. Okay. Now, delta H for this reaction is positive 572 kilojoules per mole. Calculate the delta G for this reaction at 298 Kelvin, or the standard Gibbs-free energy change. Now we know that the standard Gibbs-free energy change is equal to the standard enthalpy change delta H minus T times delta S. Right, now delta H is given to us as 572 kilojoules per mole. The temperature is 298 Kelvin. And the entropy change that we have is in joules per Kelvin per mole, but we want to calculate it in kilojoules per mole. So we're going to say 327 divided by 1000. We're going to say 327 divided by 1000 because we want to convert joules to kilojoules here. So then what does the Gibbs-free energy come out to? So it comes out to positive 474.6 kilojoules per mole. Okay. You can also say positive 475 to 3 significant figures. All right. Predict the effect of increasing the temperature on the spontaneity or the feasibility of this reaction. Explain your answer. Now over here, if I increase this temperature, so for example, over here, right? If you look at this term, if you look at the T delta S term, right? Our temperature is always positive, right? Because it's an absolute temperature, it's in Kelvin. And our delta S over here is also positive. That means that T delta S is positive. So if you look at minus T delta S would be negative, right? So as I increase the temperature, if I increase the temperature, we know that the Gibbs-free energy change will become less positive or more and more negative. So the higher the temperature, the more feasible or the more spontaneous this reaction becomes, okay? So we can say over here that if I increase the temperature, right, the reaction becomes more spontaneous or the feasibility increases. The reaction becomes more feasible, okay, or spontaneous, because you have to explain this. We know that T delta S is positive, which means that therefore negative T delta S is negative, right? And an increasing temperature, and an increase in temperature makes it more negative. makes it more negative. Of course, over here, what I mean to say, when I say makes it more negative, we mean to say that it makes delta G more negative as well. And if delta G becomes more negative as temperature increases, the reaction becomes more feasible or more spontaneous. Next, over here, we have question number 2. Now, question number 2 says, solution Y is hydrochloric acid, HCl aqueous. Solution Z is aqueous 4-chlorobutanoic acid. They've given a structural formula here. The pKa of 4-chlorobutanoic acid is 4.52. The pH of both solutions is 4.0 or 4.00. Write an expression for the Ka of 4-chlorobutanoic acid. Now we have to write the expression for the Ka of 4-chlorobutanoic acid. And first, let's actually just write down the equation for the dissociation of this acid. We have Cl, CH2 thrice, CO2H, right? And when this ionizes, it forms the conjugate base, which is the 4-chlorobutanoate ion, right? That's CO2 minus and H plus. And obviously over here, if you wrote plus H2O, here, then you would write H3O plus on the right hand side. But just for the simple expression, we're just going to write this expression here. And for the Ka for this acid, we're going to have is in the numerator, we have H plus, the concentration of H plus, times the concentration of the conjugate base, divided by the concentration of the acid. Write a mathematical expression to describe the relationship between Ka and pKa. So what is pKa in terms of Ka? What does the P over here stand for, if anyone remembers? P over here simply means the minus log to the base 10 of Ka. Calculate the concentration of H plus in solutions Y and Z. So they've told us in solution Y and in solution Z, the pH is 4.00. Now we know that the pH is simply the minus log of H plus. Now we have to find the H plus concentration. So the H plus concentration can be written as 10 to the power of minus pH. Okay? This is another expression. If you rearrange the logarithmic expression, this is what you get for the concentration of H plus. Again, that's something that you should remember. Okay, so the concentration of H plus over here is simply 10 to the power of negative 4. Okay, so we can just say 10 to the power of negative 4 or 1 into 10 to the power of negative 4 moles per dm cube. That's the concentration of H plus. Yeah. Calculate the ratio, the concentration of HCl dissolved in solution Y and the concentration of 4-chlorobutanoic acid dissolved in solution Z. Over here, if you guys remember, HCl is a strong acid. HCl is a strong acid, so we can assume that it ionizes completely. We can assume that HCl ionizes completely. So when we talk about HCl, right, when it ionizes, we get H plus and Cl minus, right? And can I say that the concentration of HCl is the same as the concentration of H plus that we got since the HCl ionized completely? Can I say that over here since it's a strong acid? Right? So we have the concentration of HCl already. We need to find the concentration of 4-chlorobutanoic acid. Now, how do we do that? Well, we have the expression for the Ka of 4-chlorobutanoic acid, right? It's right here. And we need to find the concentration of the acid in this solution. We need to find the concentration of the acid in this solution. So, over here, we know that for 4-chlorobutanoic acid, we know that the Ka is equal to the concentration of H plus times the concentration of the conjugate base divided by the concentration of the acid. And we need to find the concentration of the acid here. Now, for a weak acid, if you guys remember, for this ionization, can I say that the concentration of H plus is the same as the concentration of the conjugate base? Can I say that the concentration of H plus is the same as the conjugate base? जितना conjugate base बनेगा उतना ही H plus बनेगा इसकी ionization से, right? So I can say over here that the concentration of H plus is 10 to the power of negative 4, and the concentration of the conjugate base is also 10 to the power of negative 4. And can I say that at equilibrium, can I say that the concentration of the acid that was dissolved in the solution is the same as the concentration at equilibrium? You guys remember that assumption for weak acids, right? For weak acids, we can assume that whatever initial concentration we had for the acid is the same concentration that we have at equilibrium. So we can say that the concentration at equilibrium, that's something that we don't know. That's what we have to find here, is equal to X, okay? And this is simply equal to the Ka. Now they've given us the pKa for this acid. They've said the pKa is 4.52. They've said that the pKa over here is 4.52, right? The pKa for this acid is 4.52. So therefore the Ka is equal to 10 to the power of negative 4.52. That's 10 to the power of negative pKa. So here we can say that this expression here is equal to the Ka, which is 10 to the power of negative 4.52. And therefore, what we get is, we can get X is equal to 10 to the power of negative 8 divided by 10 to the power of negative 4.52. This comes out to what? So here we get 3.31 times 10 to the power of minus 4 moles per dm cube is the concentration of 4-chlorobutanoic acid in solution Z. So now we have to find the ratio between the concentration of HCl and the concentration of 4-chlorobutanoic acid. So that's 1 into 10 to the power of minus 4 divided by 3.31 times 10 to the power of minus 4. So what does that ratio come out to? That ratio over here comes out to 0.302. All right. Now part B of the question says, a buffer solution of pH 5 is produced by adding sodium propanoate to 5 grams of propanoic acid in 100 cm cube of distilled water. So we want to prepare a buffer solution of pH 5, okay, and we're adding the conjugate base of a weak acid, right? And we have a weak acid itself. We have 5 grams of propanoic acid, and we have 100 cm cube of distilled water. Calculate the mass of sodium propanoate that must be used to produce this buffer solution. The Ka of propanoic acid is 1.35 times 10 to the power of negative 5 moles per dm cube. So, first of all, for a buffer solution, what we need is a weak acid, right? So we have over here, we have propanoic acid. We have propanoic acid, right? That's CH3, CO2, CH2, CO2 minus plus H plus, right? And we have sodium propanoate, that is the salt of the conjugate base. That is the salt of this conjugate base. And this ionizes completely in solution to give us the conjugate base and sodium. Now, the question is asking, what is the mass of sodium propanoate that we must use? So we want to figure out the mass of sodium propanoate that we're going to use over here. Okay, that's what the question is asking. Now, in this buffer solution, they've given us the Ka, and we know that the Ka for this acid is simply the concentration of CH3, CH2, CO2 minus times the concentration of H plus divided by the concentration of the acid. Now, if you guys remember, for a buffer solution, where can I assume that all the conjugate base comes from? Where can I assume that all the conjugate base comes from? We can assume that all the conjugate base here comes from the salt. We can assume that all the conjugate base comes from the salt because the salt ionizes completely, right? So we can assume here that this is the conjugate base comes from the salt. And we don't know how much conjugate base we have. That's what we have to find. That's what we have to find over here. So let's call that X, right? Now we know the concentration of H plus because they're telling us we want to make a buffer solution of pH 5. So the concentration of H plus over here is simply 10 to the power of negative pH. So that's 10 to the power of negative 5, right? And where can we assume that all the acid comes from? Where can we assume that all the acid comes from? We can assume that the concentration of acid at equilibrium, is the same as the initial concentration of acid. We can assume that this is the same as the initial concentration of acid because, again, these two assumptions are important. First of all, the first assumption here is that because the acid only very barely ionizes, right? A very small amount of conjugate base is produced from the ionization of the acid. So we can assume that all the base comes from the ionization of the salt because this produces a lot more base. It's not that this isn't present, it's just that this is an assumption to make our calculation simpler. We can assume that all the base comes from the salt, okay? And similarly, because the acid only barely ionizes, we can assume that at equilibrium, whatever concentration of acid we have is the same as the initial concentration since it barely ionizes. And what's our initial concentration of acid? Well, they've told us that we have 5 grams of propanoic acid. So we can say over here that the number of moles of propanoic acid is equal to the mass divided by the molar mass of propanoic acid, which is, we have 3 carbons, so that's 36, plus 2 oxygens, so that's 68, right? Plus 6 hydrogens, so that's 74. So what's the number of moles of acid that we have? So here again, the number of moles of acid is equal to 0.0676 moles. Okay, so therefore we can say that the concentration of acid is the number of moles divided by volume, and that is 0.0676 divided by the volume, which is 100 cm cube. In other words, that's 0.1 decimeter cube. We're going to take the volume in decimeter cube here since we want the concentration in moles per decimeter cube. So we get 0.676 moles per decimeter cube. So that is our concentration of acid. That's 0.676. And this is equal to the Ka for the acid, which is 1.35 times 10 to the power of negative 5. So over here, if we simply do the math here, what's the concentration of the propanoate ion that we get? What does X come out to in this calculation? Okay, so the concentration of the base comes out to 0.912 moles per dm cube. Okay, this is for the propanoate ion. So we know again that the number of moles is concentration times volume. The concentration is 0.912 and the volume is 0.1 decimeter cube. So the number of moles is 0.0912 moles. And then we have to find the mass of the base. So the mass is equal to the number of moles times the molar mass. The number of moles is 0.0912 times the molar mass, which is given to us as 96. We didn't need to do the earlier calculation for propanoic acid either. They'd given it to us. So we have 0.0912 times 96. So therefore the mass is equal to 8.76 grams. So that's our final answer. Now part C of the question says, some dilute sulfuric acid is mixed with a small sample of the buffer solution described in part B. The final pH of the mixture is close to 1. Explain this observation. So if you guys remember how we define a buffer solution we have is resistant to small changes in pH. The reason why is because we have fairly high concentrations of acid and we have fairly high concentrations of the conjugate base, right? It's resistant to small changes in pH, or it's resistant to additions of small amounts of acid or alkali. But in this case, we're going from a solution of pH 5, and when we add the sulfuric acid, we go to a pH of 1. In other words, we've added too much acid. So when we add the acid to this solution, what does it react with in the buffer solution? When we add sulfuric acid, H plus reacts with what? Does it react with the acid or the conjugate base? we know that the acid, when sulfuric acid is added, right, it will react with, it'll give us a lot of H plus, which will react with the conjugate base. So over here, what's really happening is that we've added a very large amount of sulfuric acid, and therefore the buffer wasn't able to resist the change in pH. So in this case, what happened was that an excess amount of H plus was added, okay, resulting in the neutralization of the propanoate ion, right, of the conjugate base. So next over here we have question number 3. The question says define the term electron affinity. Now we know that the electron affinity is the enthalpy change when 1 mole of electrons, okay, are gained by 1 mole of gaseous atoms to form atoms or ions. Okay. Now the question isn't specifically asking for first electron affinity or second electron affinity. So it's just the enthalpy change when 1 mole of electrons are gained by 1 mole of gaseous atoms or ions. For first electron affinity, it would be atoms to form 1 minus gaseous ions under standard conditions. Now, part B says write an equation for the process corresponding to the second ionization energy of calcium. Include state symbols. Now, the second ionization energy of calcium is when we're making 2 plus ions, gaseous ions, from 1 plus gaseous ions. Remember, ionization energy is the energy needed to remove 1 mole of electrons, right, from 1 mole of gaseous atoms or ions. In this case, second ionization energy would be 1 plus gaseous ions to 2 plus gaseous ions. And obviously, 1 mole of electrons are removed. Some data relating to calcium and oxygen are listed. Select relevant data from this list for your answers to part C, D, and E. Oxygen exists as O2 molecules. Use the data in this question to calculate a value for the bond energy of the oxygen-oxygen double bond. Show all your working. Over here, if you guys remember, when we talk about bond energy, by definition, bond energy is when we break 1 mole of gaseous bonds, right? We break 1 mole of gaseous bonds to form atoms, right? So this is the bond energy. This is what we have to calculate. This is our enthalpy change X. All right. Now we have to calculate this bond energy using data in the table. And in the table, what they've given us is the enthalpy change to go directly from oxygen gas to gaseous ions, right? This is the, right? We have the energy change, right, of the reaction, or the enthalpy change when oxygen gas is converted to oxide ions, right? So let's say that over here I have oxide ions, right? Gaseous oxide ions. And that over here is simply, we can also directly convert the oxygen atoms into oxide ions, right? Now this enthalpy change here to go from oxygen molecules to oxide ions, right? That is plus 951 for 1 mole of oxide ions. But because we want to calculate the bond enthalpy, we're going to have 2 moles of oxide ions here. So this enthalpy change will be 2 times positive 951, right? Since that's the enthalpy change for half a mole of oxygen gas. Here we have 1 mole of oxygen gas to form 2 oxide ions. So that's 2 times positive 951. And this over here, right, this is the first and the second electron affinity. But since we have 2 moles of oxygen atoms, this will be 2 times the first electron affinity. That's from going from O to O minus. So that will be 2 times the first electron affinity. That's 2 times negative 142. And then 2 times the second electron affinity. So that's 2 times positive 844. The idea here is this. We want to find the bond energy for oxygen gas. That means we have 1 mole of oxygen-oxygen bonds, right? We have 1 mole of oxygen gas. And if we break 1 mole of gaseous bonds, we form gaseous atoms. That by definition is the bond energy. So that's what we have to calculate, right? That's the bond enthalpy. Now in the table, they've given us enthalpy changes corresponding to the formation of the oxide ion. They've said that the enthalpy change for formation of the oxide ion, right? That is, if we form the oxide ion directly from oxygen gas, right? 1 mole of oxide ions requires positive 951 kilojoules per mole. Now in this case, since we're forming 2 moles of oxide ions, we're forming 2 moles of oxygen atoms in the bond enthalpy. We have 1 mole of oxygen gas. We'll have 2 times positive 951. Or we can also convert the oxygen atoms into oxide ions. And since we have 2 moles of oxygen atoms, that's 2 times the first electron affinity plus 2 times the second electron affinity. So over here, we can either go directly from oxygen molecules to oxide ions, or we can first convert, we can break the bond, that's the bond enthalpy, and then we can convert the oxygen atoms into oxide ions. Those are the first and second electron affinities. So our direct route over here is corresponds to an enthalpy change of x plus 2 times negative 142 plus 2 times positive 844, right? And this is equal to 2 times positive 951. So if we do the math here, x comes out to positive 498 kilojoules per mole. Okay. Plus 498 kilojoules per mole. All right. Now, part D of the question says, suggest why the first electron affinity of oxygen is negative. Now, in most cases, the first electron affinity is exothermic. The reason why is because the energy released, right? The energy released, right? When attraction forms between the nucleus, right? Because the electrons are incoming electrons, right? So when those electrons are being added to the outer shell, there's an attraction formed between the nucleus and the incoming electron, right? So we can say that the attraction formed between the nucleus and the electron, okay, that the energy released is greater than the energy needed to overcome the repulsion. Because ultimately, think of it this way, when an electron is incoming, right, it's experiencing repulsion from the outer electrons, right? And we need to overcome that repulsion, but ultimately the energy released due to the formation of the attraction is going to be greater. So net change, we're going to have an exothermic change, okay? In most cases, the first electron affinity is therefore exothermic. So we can say that the energy released when the attraction forms between the nucleus and electron is greater than the energy needed to overcome repulsion, okay, between the outer electrons and the incoming electron. On the other hand, the second electron affinity is always endothermic. Third, fourth, so on. Any additional electron affinities are always endothermic. And the reason why is in this case, what happens is that the energy needed to overcome the repulsion, between the incoming electron and the outer electrons of the oxide ion, right? Need to overcome the repulsion between the incoming electron and the oxide ion, right? Or between the outer electrons, right, in the oxide ion is greater than the energy released. When attraction between nucleus and an electron is formed. Calculate the enthalpy of formation of calcium oxide. So using this data in the table, we have to calculate the enthalpy of formation of calcium oxide. So let's actually take this table down there, okay? So we want to calculate the enthalpy of formation of calcium oxide. All right. Now how do we do that? Now if you guys remember, this is how we use a Born-Haber cycle, right? What we have is we know that by definition, the enthalpy of formation of calcium oxide, right, is when we have calcium, right, and we have oxygen gas, we have half mole of oxygen gas, right, and the enthalpy of formation is the energy needed to form 1 mole of a substance, or the energy change to form 1 mole of a substance from its constituent element. So this is what we're trying to calculate. Now, one way of doing that is by first converting the elements into their gaseous ions, right? So by first forming calcium 2 plus ions, right, gaseous ions, and by forming oxide ke gaseous ions, right, oxide ke gaseous ions, and then by converting those gaseous ions directly into the solid. What is that enthalpy change called? When we convert gaseous, the energy change when gaseous ions are converted into an ionic solid to form 1 mole of an ionic solid. What is that enthalpy change called? That is the lattice enthalpy, right? So over here, what we can say over here is that this is the lattice enthalpy, right? And this is equal to negative 3517, right? That's the lattice enthalpy, right? By definition, the lattice enthalpy is the energy change, or the energy released when 1 mole of an ionic solid is formed from its constituent gaseous ions, right? And obviously the ionic solid is under standard conditions. So now we can say that first what we can do is we can either convert the elements into the gaseous ions and then convert the gaseous ions into a lattice, or we can directly go from elements to the ionic lattice. That's the enthalpy of formation. So here we can say that the enthalpy of formation, okay, is equal to, if we want to convert this calcium into calcium 2 plus ions, what we first need to do is we first need to atomize the calcium to form gaseous atoms, right? And then we need to ionize the calcium to form calcium 2 plus ions. Now they've given us the enthalpy change directly. They've said to go directly from calcium atoms to calcium 2 plus gaseous ions. The energy change is positive 1933. They've given us this information directly. So this is the atomization of calcium plus the first ionization energy plus the second ionization energy. So that is positive 1933, right? They've also told us the enthalpy change to go directly from half a mole of oxygen gas to oxide ions. That's the formation of oxide ions. They've also given us that enthalpy change to form oxide ions here. So here the formation of oxide ions is, for 1 mole of oxide ions, the enthalpy change over here is positive 951, right? Positive 951. So now that we formed the oxide ions and the calcium ions, right, the gaseous ions, and then they can be converted into the ionic lattice. So that will be minus 3517. So that indirect route is the same as directly going from elements to the ionic lattice. So what is the enthalpy of formation here? So here the enthalpy of formation comes out to negative 633 kilojoules per mole. Now usually they give you the ionization energies and the bond atomization energies and the bond enthalpies. But in this case, they've given us the formation of calcium 2 plus directly from elemental calcium. That is the atomization of calcium plus the first ionization plus the second ionization. Similarly, for oxygen, they've given us the formation of oxygen directly from elemental oxygen. They've given us the formation of oxide ions directly from elemental oxygen. Otherwise, this would be half the bond enthalpy of oxygen, or atomization of oxygen, plus the first electron affinity plus the second electron affinity. Okay. Now, the lattice energy of lithium fluoride is negative 1022 kilojoules per mole. Identify the factor that causes the lattice energy of calcium oxide to be more exothermic than that of lithium fluoride. Explain why this factor causes the difference in lattice energies. Now for calcium oxide, our lattice enthalpy for calcium oxide is negative 3,517 kilojoules per mole, right? Whereas for lithium fluoride is negative 1,022. So what factor causes the lattice energy of calcium oxide to be more exothermic? We know that it's much more exothermic than lithium fluoride, right? There's two factors that affect the magnitude of the lattice enthalpy. The smaller the ions, the more exothermic it is, as well as the greater the charges. Now in lithium fluoride, the charges are +1 and -1, whereas in calcium oxide, you have charges of +2 and -2. Now, even though lithium is much smaller than calcium, right? Remember, the smaller the ion, the more exothermic it is. But in this case, we have a larger ion, but it's still way more exothermic. The reason why is because because calcium and oxide both have a greater charge, what we have is we have a much more exothermic lattice enthalpy. Okay? Because if we were just looking at the size, it would be less exothermic because calcium is larger than lithium, okay, significantly. However, because we have a much greater charge for calcium and oxide, right, we can say that the charge over here is the main factor. So the ionic charge, right, is, or you can say the charge density, that is the charge per unit volume, okay. And the reason why the charge makes it more exothermic is because, right, of the ions in calcium oxide is greater, right? Therefore, there are stronger electrostatic forces of attraction between the oppositely charged ions, between the cations and the anion. All right, the next question that we have here is question number 4. Separate samples of 0.02 moles of calcium carbonate and 0.02 moles of barium carbonate are heated until completely decomposed to the metal oxide and carbon dioxide. State which of these two group 2 carbonates requires the higher temperature before it begins to decompose. Explain your answer. So which of these oxides is more thermally stable, or carbonates is more thermally stable? Barium carbonate or calcium carbonate? Which is more thermally stable? Whichever one is more thermally stable requires a higher temperature. If it's more stable, more heat is required. And we know that the stability of carbonates, the thermal stability, increases down the group. So barium is lower down the group than calcium. Therefore, barium carbonate is more thermally stable. Okay. So we can say that barium carbonate will require the higher temperature, right? And the reason why is because, right, because the barium 2 plus ion, right, 2 plus ion has a larger radius, and therefore a lesser or a smaller charged density, right? So it won't distort the anion as much. Yes, exactly. It has a lesser charge density, right? And therefore, and hence, it does not distort, okay, or it has a lower polarizing power, so it results in lesser polarization, okay. It polarizes or distorts the carbonate ion to a lesser extent. In this case, remember, okay, they both have the same charge. Calcium and barium. So in this case, it'll be the radius that affects it, right? Since the charge is the same on both, right? Because barium has a larger radius, right? Same charge but larger radius, it means that the charge per unit volume is lesser. Same charge but over a larger volume, which means lesser charge density. And the lesser the charge density, the lesser it polarizes the anion, and therefore the more difficult it is for the anion to decompose, or for the carbonate to decompose. All right. After decomposition is complete, the 0.02 mole sample of calcium oxide is taken and added to 2 decimeter cube of water. A solution is formed with no solid present. Dilute sulfuric acid is then added dropwise until a precipitate is seen. The same procedure is repeated with the 0.02 mole sample of barium oxide using the same concentration solution of dilute sulfuric acid. Identify the sample to which most sulfuric acid must be added to cause a precipitate to appear. Explain your answer. You should refer to the solubilities of the precipitates and relevant energy terms in your answer. Now what we're doing over here, guys, is we're first taking an oxide. Okay, and we're adding it to water. Okay, we're adding it to water to form the hydroxide. Okay, and then when the hydroxide is reacting with sulfuric acid, the hydroxide is reacting with sulfuric acid to form the sulfate, and H2O. So this is the reaction procedure that we're doing. We're doing the same thing for calcium oxide and barium oxide. Okay, the question is, in which case will more sulfuric acid need to be added to cause a precipitate to appear? In other words, the question is asking which sulfate is going to be more soluble, right? The more soluble the sulfate, the longer it will take for the precipitate to appear. The less soluble or the more insoluble it is, the quicker the sulfate will form. So in this case, right, which sulfate is more insoluble? Now over here, since barium sulfate is, we know that sulfate solubility increases down the group. Okay, sulfate solubility increases down the group. So barium sulfate is more insoluble, so it'll form faster. When you're adding sulfuric acid, barium sulfate will form almost immediately, whereas calcium sulfate will take longer to form because it's more soluble. So more sulfuric acid will be needed for the formation of calcium sulfate. Okay, so the answer over here is the sample for which more sulfuric acid needs to be added is for calcium. Okay, the calcium oxide sample, okay, or calcium sulfate sample will take longer. And the reason why is because calcium sulfate is more soluble in water than barium sulfate. So we know that sulfate, right, this is because the solubility of sulfates decreases down the group. So in this case, again, calcium sulfate is more soluble, so we need to add more sulfate to it in order for it to precipitate. And this is because the solubility of sulfates decreases down the group as we have to talk about enthalpy changes, and this is because the enthalpy change of solution becomes more endothermic down the group, okay, for sulfates. Right? The reason why this happens is because as you go down the group, right, both the lattice enthalpy, right, and the hydration enthalpy, okay, become less exothermic, okay, but the change for the enthalpy change of hydration is greater. So I'll explain this algebraically. See, what you have is, if you have a solid precipitate, right, if you form gaseous ions, that is the negative lattice enthalpy. By definition, right, that is the negative lattice enthalpy. Right? And if those gaseous ions dissolve to form aqueous ions, right, that is enthalpy of hydration. And the overall change from solid to aqueous is delta H solution. So we can say over here, okay, that the delta H solution is equal to the delta H of hydration minus the lattice enthalpy, right? Now in this particular case, think of it this way, right? What we're saying is that what we're saying over here is that the delta H solution is becoming more endothermic because the solubility is decreasing. Now, if the delta H solution is becoming more endothermic, it means that hydration is actually changing by a bigger amount. Hydration is becoming less exothermic. Lattice enthalpy is also becoming less exothermic, right? But because hydration is shifting by a greater amount, this delta H solution is moving further upwards. So because the change in hydration is greater in this case, the delta H solution becomes more endothermic, okay? Intuitively, the idea is that hydration tells you how soluble something will be or how much the formation of the aqueous ions will be favored relative to the lattice enthalpy. Now, if the hydration enthalpy is becoming even more less exothermic or is being even less favored than the lattice enthalpy, it means that the solubility is being less favored, okay? On the other hand, if lattice changes by a greater amount and hydration doesn't change as much, it means that the solution becomes less endothermic. So that is the case that you have with oxides and hydroxides, for example. All right. Calculate the mass in grams of carbon dioxide produced by the decomposition of 0.02 moles of calcium carbonate. So here what we have is we have calcium carbonate, right, decomposing to form calcium oxide and carbon dioxide. And we have 0.002 moles of this, 0.02 moles. So therefore 0.02 moles of carbon dioxide are produced. So we can say that the mass of carbon dioxide is the number of moles times the molar mass. So that will be 0.02 times the molar mass of carbon dioxide is 44. And therefore, this will be equal to 0.88 grams. The next part says, calculate the minimum mass in grams of propane that would, on complete combustion, produce the same mass of carbon dioxide calculated in C part 1. Give your answer to 3 significant figures. So here they're saying if I had propane, so propane would be C3H8, right? If it combusts to produce carbon dioxide, right? So here we have the equation for the combustion of propane. So we have 3CO2 and 4H2O, leaving us with 5 oxygens here, right? And they're saying, what is the mass of propane that I would need to get the same mass of carbon dioxide? In other words, what I want to do is I want to produce 0.02 moles of carbon dioxide, or 0.88 grams. We have the number of moles here as well. I want to produce the same number of moles of carbon dioxide. So how many moles of propane would I need? We want to find the mass of this. So we know that for every 1 mole of propane, 3 moles of carbon dioxide are produced. For every 1 mole of propane, 3 moles of carbon dioxide are produced. So if I have 0.02 moles, how many moles of propane do I have? That's 0.02 divided by 3, right? If we cross multiply. So that would be 0.006666, right? Moles of propane. So then what's the mass of propane? The mass is simply the number of moles times the molar mass. So that is 0.02 divided by 3 times the molar mass is 44, right? C3H8. That's 36 plus 8, so that's 44. So the mass of propane over here would be 0.293 grams. Next question. Manganese chloride is a complex ion. Deduce the oxidation state of manganese in this complex ion. Now we know that the chloride has an oxidation state of -1, and we have 4 chloride ions, right? Manganese, we don't know, that's X. And the overall oxidation state is just the overall charge, that's -2. So X over here is equal to +2. So that's the oxidation state of manganese. So here we have manganese 2 chloride. The manganese 2 chloride complex does not contain any 180-degree bond angles. Draw a 3-dimensional diagram to show the shape of the MnCl4 2- complex. State one bond angle on your diagram. So if it's a 4-coordinate complex that doesn't have any 180-degree bond angles, what would the shape be? There's only 2 4-coordinate complexes that we've learnt about, right? One is square planar. In square planar, what you do have 180-degree bond angles like right here, right? Between the two opposite ligands. So in this case, we don't have a square planar complex, so it must be a tetrahedral complex. Okay, it must be a tetrahedral complex. So here the shape would look like this. Okay, we have Cl, 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 right? The overall charge on this complex ion is 2-, and the bond angle is 109.5 degrees. All right. A solution of cobalt 2 sulfate contains the complex ion cobalt hexaaqua. A solution containing this complex ion is reacted separately with an excess of each NaOH aqueous, NH3 aqueous, and NaCl aqueous. Write an equation for each of these reactions. State one observation that can be made immediately after the reaction, including the color and the state of the cobalt containing product. Now, first of all, let's actually recall the colors of these solutions. We know that cobalt hexaaqua is a pink solution. Okay, cobalt hexaaqua is a pink solution. Okay, so you should know this. It's a pink solution. Okay, now when it reacts with sodium hydroxide, we form cobalt hydroxide. Okay, which is a blue precipitate. So the equation for that would be this. We have COH2O6, right? 2 plus reacting with hydroxide ions to form CO, H2O4, and OH twice, right? And obviously 2 of the waters are released. Alternatively, you can also write in the products, you can also write this. You have cobalt hydroxide and 6H2O. Okay, these are both acceptable products. Okay, these are both acceptable products. Ultimately, what you do end up forming is a neutral precipitate. And the observation here is that you form a blue precipitate. Okay, cobalt hydroxide is a blue precipitate, cobalt 2 hydroxide. Okay, with excess ammonia, what happens is that for cobalt, all 6 of the water molecules are exchanged by ammonia. So this is a ligand exchange reaction. Okay, so all six of the cobalts are exchanged by ammonia over here, and what you end up making is CO, NH3, 6, 2 plus, and 6H2O. Okay, and this guy over here, when you have cobalt hexamine, this is a brown solution. Okay, this is a brown solution. The first reaction here, you can say yellow-brown, you can say yellow as well. Okay. Now over here, what you have is this reaction would be classified as a precipitation reaction. Even though it is a ligand exchange reaction, because you're seeing a precipitate form, we would call this a precipitation reaction. Whereas the second reaction is a ligand exchange reaction. Okay. And when sodium chloride is added, right? Now this cobalt hexaaqua complex, right, will react with 4 chlorides and form a tetrahedral precipitate, that is cobalt chloride. Okay, COCl4 2- and 6H2O. Okay, and this solution over here is a blue solution. Okay, cobalt chloride is a blue solution. And the reason why we don't have a 6-coordinate complex here and we have a 4-coordinate complex instead is because chloride ions are much larger ligands than water molecules, because chlorine is a much larger atom. So there's not enough space to have 6 chloride ions around the central metal ion. Okay. Name the type of reaction that occurs in B part 3. So this reaction is called a ligand exchange reaction. Okay. So it's a ligand exchange reaction. Cobalt forms the complex ion CONH3 twice, En twice, where En is obviously a bidentate ligand. The abbreviation EN is used for the bidentate ligand 1,2-diaminoethane. The complex ion shows both geometrical and optical isomerism. Define the term bidentate ligand. Now, a bidentate ligand is a species, right? First, we just define ligand. A ligand is a species that forms dative bonds, right, with a central metal ion. But a bidentate ligand is a species that donates two lone pairs of electrons, okay, to form to a central metal ion, right, to form two dative covalent bonds, to a central metal ion or atom, okay? All right. Draw the three-dimensional diagrams for the two optical isomers of this particular complex. Now, if you guys remember, they're saying this complex shows cis and trans geometric isomerism as well as optical isomerism. Now, first of all, my question is, will the trans isomer show optical isomerism? No, right? The trans isomer doesn't show optical isomerism because it's perfectly symmetric. So whenever you have two bidentate ligands and two monodentate ligands, you can have cis and trans isomerism, but the trans isomer doesn't show optical isomerism, whereas the cis isomer does. Okay, the trans isomer doesn't show optical isomerism, whereas the cis isomer does. So in this case, we must have the cis isomer present. Okay, the cis isomer shows optical isomerism. So if we do the cis isomer here, what do we have? Well, what we have here is the two NH3s must be 90 degrees from each other. So we have NH3, and then we have N, and then we have N and N over here, right? And the optical isomer or the enantiomer for this guy, which is going to take the mirror image. So now the NH3s, which are on the right or the near side, right, will now be on the left. That'll be NH3 and NH3, and then we have the two bidentate ligands over here. Okay. So again, the cis isomer is not symmetric. Okay, so this is what shows optical isomerism. The next question that we have here is question number 6. An excess of sodium iodide is added to a solution of copper 2 sulfate. Iodine and a white precipitate of copper 1 iodide are formed. Write an equation for this reaction. So what we have here, we're starting with copper 2 sulfate, right? CuSO4. And this reacts with sodium iodide. To form copper 1 iodide. So that will be CuI plus iodine. And obviously, we're also going to we have sodium and sulfate left over. So that will be sodium sulfate, right? So this is the balanced equation, yes. Okay. So now that we form sodium, now we need to balance this equation. Now, how do we balance this? We know that copper is being reduced from +2 to +1, right? Since we have copper 2 sulfate, and we're forming copper 1 iodide, right? Now, what that means over here is that iodine is being oxidized from -1 to 0. In other words, copper 2 over here is copper 2 sulfate is the oxidizing agent, and iodide is the reducing agent. Now, can I say over here that I- is undergoing oxidation, right? And Cu2 plus is undergoing reduction. So here, can I say that for every 1 mole of copper 2 plus, I'll have half a mole of iodine, right? For every 1 mole of copper 2 plus, I'll have half a mole of iodine, right? Since the 1 electron is being lost here and 1 electron is being gained here, this is how we're going to balance this equation, right? So what we have over here is if we multiply top and bottom by 2, right, just to get whole numbers, what do we get? What do we get? For every 2 moles of copper 2 plus, for every 2 moles of copper 2 plus, right, we have 1 mole of iodine. For every 2 moles of copper 2 plus, we have 1 mole of iodine. Okay? And now we're just going to balance out the rest, right? If we have 2 coppers on the left hand side, we're going to have 2 coppers on the right hand side. That gives us a total of how many iodines? We have 2 plus 2, so that will be 4, right? And then over here, since we have 2 sulfates here, we're going to have 2 sulfates on the right hand side and 4 sodium. So that will be 2Na2SO4. Again, now we have to explain why the copper 2 sulfate solution is colored. In other words, why are solutions of transition element ions or complexes usually colored? Okay, and the reason why is because what happens in transition element in solutions of transition element ions is that first of all the d orbitals, okay, the d orbitals are split, okay, into 2 different sets, right, into 2 different sets of orbitals, right, with different energies, right, with different energies. And the difference in energy, right, the difference in energy, we just call that delta E, corresponds to a certain frequency of visible light, right, that is absorbed, right, resulting in the promotion or excitation of the electron, from lower energy d orbitals to higher energy d orbitals to higher energy, right? And the complementary color is observed to the absorbed color. The complementary color is observed. Suggest why the precipitate of copper 1 iodide is white. In other words, why is the copper 1 iodide not colored? Now, if you guys know, copper की जो electronic configuration होती है, it is argon 3d10 4s1. So then copper 1 plus has the configuration argon 3d10. So here, are there any partially filled d subshells for excitation to occur? Now for copper 1 plus, the d subshell or all the d orbitals are completely full. The d subshell is completely full, right? So we can say that for copper 1 plus, right? For copper 1 plus, the configuration is argon 3d10, right? Which means that, right, all the d orbitals are full, right? Which means that no excitation or no absorption takes place of an electron. There's no space for the electrons to get excited, okay? So what we have is we have no absorption of visible light, okay? All right. Use suitable E0 values from the data booklet to predict whether iodide ions can reduce copper 2 plus to copper 1 plus under standard conditions. Explain your answer. Now here from the data booklet, we have these following half equations. Okay, we have these 2 half equations from the data booklet. Okay, and the question is asking whether iodide ions can reduce copper 2 plus to copper 1 plus. So what we're saying is if we were to start with iodide ions, our reactants are iodide ions and copper 2 plus ions. So if I started with iodide ions, right? If I started with iodide ions over here, okay, and let's just balance the electrons, so just multiply 2 electrons here. And I also have copper 2 plus ions. right? What would I get? My starting react to form copper 1 plus. The E for this reaction is negative 0.54 and the E for this reaction is positive 0.15, right? Because over here we're taking the reverse reaction, right? We're starting with iodide ions. That's my starting reactant. Now, would these two react आपस में? Would iodide be able to reduce copper 2 plus? What's the overall EMF over here for this reaction? What is the overall EMF for this reaction? Right? The overall EMF for this reaction would be negative 0.39 volts, right? Which means that the question is saying, predict whether iodide ions can reduce copper 2 plus ions. And the answer over here is no. Because the E naught for this reaction is equal to negative 0.39 volts, right? Which means that, right, the reaction is not spontaneous. Negative E naught means positive delta G, so it's a non-spontaneous reaction. An excess of sodium iodide is added to copper 2 sulfate solution. Copper 1 iodide forms as a precipitate. After precipitation, Cu1 plus is much lower than 1 mole per dm cube. Use this information and your answer to C to explain how the relevant electrode potentials change and hence why iodide ions can now reduce copper 2 plus ions. So, if the copper 1 plus concentration decreases substantially, what happens to this equilibrium? If the copper 1 plus concentration decreases substantially, right, what happens to the copper equilibrium? What happens is that the equilibrium shifts to the right. So then what happens to the EMF or the E naught for this electrode? Right? The Cu2 plus / Cu plus equilibrium shifts to the right, right? Making the E more positive for that reaction. And if it increases a lot, if it becomes a lot more positive, right? If this keeps on becoming more and more positive, what happens to the overall EMF? If this becomes more positive, right? Eventually what happens is the reaction becomes more and more spontaneous. So as copper 1 plus keeps on precipitating and the concentration of copper 1 plus decreases, the equilibrium keeps shifting to the right, and eventually this E naught, right, this E becomes more positive than 0.54. So it becomes more positive than 0.54 volts. And eventually, once it becomes more positive than 0.54 volts, right, then the overall reaction would become spontaneous. Okay? All right. The next question that we have here is question number 7. All right. The question says the structure of phenylethanoic acid is shown. Give the number of different peaks in the carbon-13 NMR spectrum of phenylethanoic acid. So how many different types of carbon atoms do we have here? We have 1, 2, 3, right? These two are the same, so that's 4, right? This is symmetric. These two are the same as well, so that's 5. And then we have 6. So we have 6 different types of carbon atoms here, so we're going to see 6 different peaks in the carbon NMR spectrum. Phenylethanoic acid, ethanol, and phenol can all behave as acids. Compare and explain the relative acidities of these 3 compounds. Now, the least acidic over here must be ethanol, right? That's the least acidic one. And what's the most acidic here? When we talk about a carboxylic acid versus phenol, carboxylic acids tend to be more acidic, okay, than phenol. The phenol is also acidic, but not as acidic as carboxylic acids. Now explain why. Okay. Now, so first let's start with why is phenylethanoic acid is the strongest acid, right? We know that phenylethanoic acid, right, is the strongest acid, right? Because you have the phenylethanoate ion, right? That's the conjugate base. That's the conjugate base is the most stable conjugate base. Due to the electron withdrawing effect of the carbon double bond oxygen, right? C double bond O. Phenol, right? The phenoxide ion is next, right? Because it's also stabilized, but it's stabilized to a lesser extent, okay? Is stabilized due to the delocalization of the lone pair of electrons into the benzene ring. Right? And lastly, we know that ethanol is the weakest, right? Ethanol is the weakest, okay? Acid, because the electron donating effect of the ethyl group in the ethoxide ion, right, makes the conjugate base less stable, right? Makes it less stable, makes it unstable. Okay. Phenylethanoic acid can be synthesized using benzene as the starting material. In the first stage of this synthesis, benzene reacts with chloromethane. Chloromethane is CH3Cl, right? In the presence of an AlCl3 catalyst to form methylbenzene. Chloromethane reacts with AlCl3 to form two ions. One of these is the carbocation CH3+. That's your electrophile, right? This mechanism is electrophilic substitution. So in the first stage, we're going to use chloromethane, right? And it will react with the catalyst to generate the electrophile. So we're going to form CH3+ and AlCl4-. Okay. Then once we have this positively charged electrophile, then we can have the electrophilic substitution mechanism take place. So we have to draw the mechanism of this methyl ion with benzene to form methylbenzene. Now in this mechanism, first what happens is that a lone pair of electrons is donated from the benzene ring. Make sure the arrow is drawn from the ring to this cation here, right, to form a carbocation intermediate, right? The ring is broken temporarily, where you have an H and a CH3. And then the electrons from the CH bond on the benzene ring go back to reform that ring, and the H plus is released. So the CH3 substitutes for the H over here. So we actually end up releasing H plus. Okay. A 3-step synthesis of phenylethanoic acid from methylbenzene is shown. State the reagents and conditions for step 1. Now over here in step 1, what you have is the CH3 is being converted into a CH2Br. So this is not benzene, this is not substitution on the benzene ring. This is substitution of a saturated CH by bromine. So this is free radical substitution. So the reagents and conditions for this would be Br2 and UV light. Right, this is free radical substitution, right? What we have in alkyl groups or alkanes over here. The hydrogen is being substituted by a bromine on a saturated carbon atom. Okay. Suggest the structure of compound Q. Now, for phenylethanoic acid, what we're doing is here, if you notice, we're increasing the number of carbon atoms by 1. So what can we do to this bromoalkyl group to increase the number of carbon atoms by 1, which we can then use to form a carboxylic acid that has 1 extra carbon? We can use, if you guys remember, we can use KCN and ethanol, right? What we can do here is we can convert the bromoalkyl group into a nitrile. We can say over here that the bromine can be replaced by a cyanide group. So we make a nitrile here. So now we have 1 extra carbon atom, right? We have 1 extra carbon atom. And for that reaction, we're going to use KCN and ethanol and heat under reflux. All right, or we can just say heat over here. And then the nitrile can be converted into a carboxylic acid. That reaction is called the hydrolysis of nitriles. And for that, we're going to use HCl aqueous, or we can say dilute HCl and heat under reflux. Right, that's hydrolysis of nitriles to form a carboxylic acid. Now over here in both of these cases, it's heat under reflux, but they'll accept heat in both. Okay. But in some cases, they explicitly expect you to know heat under reflux. Like for example, when you're talking about oxidation of primary alcohols to carboxylic acids, you have to say under reflux, because heating and distilling will give you aldehyde and heating under reflux will give you acid, right? So in some cases, they explicitly expect you to say heat under reflux. Otherwise, in most cases, it's just better to say heat in case you've forgotten, right? If you're not sure if it's heat under reflux or just heat, just always say heat, okay? Draw the structure of an organic byproduct that forms in step 1. So they're saying in step 1, when you have free radical substitution, you can have other organic products form. So one possible organic product that you can have is if you have further substitution take place, right? If you have further substitution take place, right, what you can have is that on the benzene ring, right, instead of 1 bromine atom substituting, you can also have 2 bromine atoms substitute. So that is another possible product of the free radical substitution reaction. Okay. You can also have 3 bromines here. For any further substitution product over here would be accepted. Okay. All right. The next question that we have here is this. Phenylamine and ethylamine can be distinguished by adding aqueous bromine. State what is seen when aqueous bromine is added to phenylamine. Now, if you guys remember, whether you have phenol or phenylamine, when you add aqueous bromine to it, what do we see? We see decolorization. We see decolorization of the aqueous bromine, right? And we also see a white precipitate of 2,4,6-tribromo-phenylamine. Suggest what is seen when aqueous bromine is added to ethylamine, right? No change is observed, or no observation here, okay? And the structure of the organic product when excess of aqueous bromine is added to phenylamine. Now, if you guys remember, for phenylamine, what we have is when NH2, right? When it reacts with, phenylamine reacts with aqueous bromine, you have this tri-substituted product, okay? And this is because phenylamine is highly reactive due to the overlap of the electrons on the nitrogen, the lone pair into the benzene ring, right? So with phenol or phenylamine, if you have an OH here or an NH2, you form this white precipitate of 2,4,6-tribromo-phenylamine in this case, or with phenol it's 2,4,6-tribromo-phenol, okay? And that's why the bromine is decolorized and a white precipitate is observed, okay? This is a white precipitate here. All right. Name the product that you have drawn in part C. This product is called 2,4,6-tribromo-phenylamine. All right, the next question that we have here is question number 9. Compound T is made by a three-stage synthesis. In stage 1, phenylethanoic acid reacts with a suitable reagent to form compound R. So phenylethanoic acid, right? This carboxylic acid is being converted into an acyl chloride. Suggest a suitable reagent for stage 1. Well, the reagent that we can use is PCl5, right? In stage 2, compound R reacts with ethylamine to form compound S. Name the functional group formed in stage 2. So here what we have is we have an acyl chloride reacting with an amine to form what kind of a linkage here? What is this linkage called when you have the CONH and R groups on either side? This functional group is called an amide linkage, right? So this is an amide. Okay. What is the other product formed in this reaction? If you guys remember, C double bond OCl combines with an amine to form what? You're forming this linkage, right? The CONH bond, right? And what else are you forming? You're also forming HCl, right? This is a condensation reaction. So the other product in this reaction is HCl. Okay. In stage 3, compound S reacts with a suitable reagent to form compound T. So the amide is being reduced to an amine. So what is a suitable reagent for stage 3? Right? This is the reduction of an amide to form an amine. So for this, you have to use lithium aluminum hydride, okay? But it has to be anhydrous. So you can say anhydrous lithium aluminum hydride, or you can say lithium aluminum hydride in dry ether, okay? Either one is acceptable, okay? They just want the formula of the reagent. So in this case, they'll just accept LiAlH4, okay? They haven't asked about the conditions. If they asked about the conditions, you would say LiAlH4 in dry ether, okay? In dry ether and heat, okay? Name the type of reaction. This is obviously a reduction reaction, okay? Amides and carboxylic acids can only be reduced using lithium aluminum hydride, okay? The relative abundance of the molecular ion peak in the mass spectrum of ethylamine is 62. Calculate the relative abundance of the M+1 peak in the mass spectrum. Now, if you guys remember, the ratio between the M and the M+1 peaks is equal to 100 divided by 1.1 N, right? Where N is the number of carbon atoms. Now, over here for ethylamine, right? We know that we have 2 carbon atoms, so N is equal to 2, right? Now, we want to find the relative abundance of the M+1 peak, and they've said that the relative abundance of the M peak is 62. So we have 62 divided by X, that's what we have to find, and this is equal to 100 divided by 1.1 times 2. So that is 2.2. So then what is X equal to? X is equal to 2.2 times 62 divided by 100. So here X comes out to 1.36. So that's the relative abundance of the M+1 peak. The mass spectrum of compound T contains several fragments. The mass to charge values of 2 of these fragments are 29 and 91. Draw the structures of the ions responsible for these peaks at 29 and 91. So if you look at compound T here, okay, this is compound T. So I'm just going to take a little bit of a screenshot here, right? We have compound T over here. And they want to know what fragments are responsible. They want to know what fragments are responsible for the peaks at 29 and 91. Okay. So now at 29, what peak do you think is responsible for the peak at 29? A very common peak that we have at 29 is, the CH3CH2, right? This ethyl group over here. Okay, this is a very common fragment. So CH3CH2, right? This cation is responsible for the peak at 29. Now, what about 91? Now, first of all, guys, remember that a benzene ring is 77. A benzene ring over here is 77. Okay? So then, what do we have next? We have 77 plus a CH2. A CH2 is how much? CH2 would be 14, right? So what if the bond broke over here? What would this fragment have a mass of? A 77 C6H5 plus a CH2. That would be 91. So the fragment here would be C6H5CH2 plus. All right. Next part. The proton NMR spectrum of compound T shows hydrogen atoms in different environments. 6 of these environments are shown on the structure using the letters A, B, C, D, E, and F. Using the letters to A, B, C, D, E, and F to answer the question that follow. The question relates to the proton NMR spectrum of T. Proton D does not cause splitting for proton C or E under the conditions used. Okay, so the proton on the nitrogen atom does not split the neighboring protons. Each answer may be one or more than one of the letters A, B, C, D, and F. Now let's look at the table over here, right, that we have for the proton NMR spectrum. Now part 1 says, identify the proton or protons with a chemical shift in the range 6 to 9. So in the range 6 to 9, what proton would shift in that range over here? The range 6 to 9 is the proton attached directly to the aromatic ring. So that would be proton A. That would be proton A over here, right? A hydrogen atom on an aromatic ring. Here AR stands for the benzene ring. Okay? Right? That would be the proton A. Identify the proton whose peak will disappear if D2O is added. Which peak disappears when D2O is added? Right, when D2O is added, you have the isotope that has an even nucleon number, and it substitutes for either an NH proton or an OH proton. In this case, you don't have an OH, you only have an NH. So the NH peak will disappear. So that will be proton D. Okay. Identify the proton or protons whose peak is a triplet. So the question here is, for which of these protons has neighboring carbon with 2 protons? Now, if you look at proton C, right, if you look at proton C, the neighboring carbon has 2 protons. So it will be split into a triplet. Similarly, proton B, right, the neighboring carbon C has 2 protons. So B will also be split into a triplet, right? And if you look at proton F, right, the neighboring carbon E also has 2 protons. Remember, if you have a triplet split, right, if you have a triplet, right, that means that n plus 1 is equal to 3. In other words, the neighboring carbon over here must have 2 protons. The neighboring carbon must have 2 protons. Okay, that's the pattern that you see. So the protons over here, right, that would be split into a triplet would be B, C, and F. Okay. B, C, and F. And the proton or the protons with the lowest chemical shift. So which proton would have the lowest chemical shift over here? It would shift in this alkyl group range. That would be proton F, right? That is the one that will shift in the very low range because it's just a proton. That carbon is just attached to an alkyl group, right? So that will be in the range 0.9 to 1.7. So the lowest chemical range over here will be proton F. All right, the last question that we have over here is question number 10. Valine and lysine are amino acids. The structures of these amino acids can be found in the data booklet, right? Obviously, we don't have a data booklet anymore, so I'll give you the structures of valine and lysine. The isoelectric point of an amino acid is the pH at which it exists as a Zwitter ion. The isoelectric point of valine is 6.0. The isoelectric point of lysine is 9.7. So the isoelectric point is the pH at which these amino acids are said to be neutral. Okay, neutral in terms of charge. Okay, if the pH is below the isoelectric point, then the amino acid will be positive. If the pH is above the isoelectric point, then the amino acid will be negative. Now valine looks like this. If you look at the structure of valine, okay, I'll give that to you. Okay, this is the structure of valine from the data booklet. Okay. Now, at pH 6, they're saying it exists as a Zwitter ion. So what exactly is a Zwitter ion over here? A Zwitter ion is when you have the carboxylic acid proton is transferred to the amine group on the same amino acid, right? So the obviously at pH 6, valine is just a neutral, overall neutral Zwitter ion. So what we end up with in the Zwitter ionic form, valine looks like this, right? You have an NH3 plus and a O minus. So here we have the Zwitter ionic form for valine, okay? Now part B says a solution of lysine is produced with pH 9.7. Again, this is the isoelectric point of lysine. In other words, lysine is said to be neutral at 9.7. Okay, it just exists in its Zwitter ionic form. Okay, now the structure of lysine over here looks like this. Okay, the structure of lysine over here, I'll draw it on the side, looks like this. Okay, what we have for the structure of lysine is we have, again, a carbon that's bonded to an NH2, right? And that carbon is also bonded to this guy over here. And then what you have is this. You have CH2 times 4, and then you have NH2. Okay, this is the structure of lysine. Okay. Now the question here is this, right? The question is asking, okay. Now obviously when we talk about pH, when we talk about the Zwitter ion, obviously the lysine Zwitter ion looks like this, right? At 9.7, that's the isoelectric point, and the Zwitter ion will look like this, right? You'll have this, the transfer of a proton, and you'll have O minus here and NH3 plus here. Now, when dilute sulfuric acid is added slowly until the pH of the solution is 1.0 or 1.0, the sulfuric acid reacts with lysine to produce different organic ions that are not present in significant concentrations at 9.7. Draw the structures of three of the organic ions that are formed during the addition of sulfuric acid in the boxes. Draw the organic product present at pH 1.0 in box C. Now again, this is the Zwitter ionic form of lysine at pH 9.7. That's the isoelectric point. So it's neutral, right? It doesn't have a net charge at pH 9.7. Now as I decrease the pH, right, that means I'm increasing the H plus concentration, right? I'm increasing the H plus concentration. Now I'm going to have a cation because the pH is below the isoelectric point. So there's more H plus present. So that means that the carboxylic acid will now definitely be protonated, right? The carboxylic acid will be protonated here, right? And I can either have a positive charge on this NH3, all right, in which case the other NH2 is uncharged, right? In which case the other NH2 is uncharged. And the other possibility that I have is that the positive charge is on the NH3 in the R group, right? On the NH2 in the R group. In other words, on the side chain over here. So what we have is we can have CH2 times 4, and then you can have an NH3 plus here, right? So we can have a 1 plus ion, right? In which case either this amine gets the positive charge or this amine gets the positive charge. And they're saying if we reduce the pH drastically, then what do you think the charge on the amino acid will be? Will it be 1 plus or will it be 2 plus? If I have a very, very low pH, a pH of around 1 over here, then what will happen is that both the amine groups will get protonated. Okay. So what you'll have here is you'll have an NH3 plus here, and you're going to have an NH3 plus over here as well. Another way to visualize this, guys, that rather than looking at the Zwitter ionic form, let's just look at the regular form of this amino acid. So what we have here is we have an NH2 and an OH. Now this is the structure of the amino acid at pH 9.7. It's neutral, right? You can say it's a Zwitter ion which has O minus and NH3 plus. Again, electrically the overall charge is still 0. Okay, but if I decrease the pH, if I increase the H plus concentration, right, we know that the amines are what's going to react with H plus. H plus will react with the base. So what will happen is that the amine groups will accept a proton. So either this amine can accept a proton making this NH3 plus, or this amine can accept a proton, making this NH3 plus. Now, if the pH is very, very low, if I have a very large concentration of H plus, then both the amines will accept a proton. So you'll get an overall, you'll get a cation with a charge of +2. Draw the structure of the dipeptide valine lysine or val-lys. The peptide bond should be shown fully displayed. Okay, the peptide bond is basically the amide linkage. Okay. Now, what we have here is we have valine. Okay, we have valine over here. Okay, that has this structure, and we have over here lysine. Okay, and lysine has the following structure. It has an NH2. Okay, it has an NH2, and it has this guy over here. Right, it has a CH. It has 4 CH2, so that's 1, 2, 3, 4. Right, we have CH2, 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 and then you have an NH2. Okay. Now, in the dipeptide valine lysine, in the way it's written, guys, whenever it says valine lysine, it means that the valine ka NH2, right? The valine ka NH2 is unreacted. Whenever you're writing a dipeptide, okay, or a polypeptide, it's always in the order N to C. So when I say valine lysine, it means that we're going to start with the N of valine on the left-hand side, and we're going to end with the carboxyl group of lysine on the right-hand side. So if we form an amide linkage here, what the amide linkage is formed between the carboxyl group on valine and the amine group on lysine. Okay, between the carboxyl group of valine and the amine group of lysine. So this is the amide linkage that will form here. So the dipeptide that we're going to form here will look like this. The dipeptide that we form here will look like this. We have NH2. Okay, then we have this guy. Then we have the double bond, right? O over here. Then this will bond to the N and the H, right? This carbon, the carboxyl carbon will bond to the nitrogen from the amine. That's NH. Then we have this guy over here that has CH2 4 times. So we have 1, 2, 3, 4. And then we have an NH2. And then we have this carboxyl group. Okay, so that is the dipeptide valine lysine. All right. On the other hand, if it was lysine valine, then it would be the lysine ka NH2 that's unbonded and the valine ka CO2H. So valine lysine val-lys is not the same as lys val. Okay, because the order matters over here. So this is your answer.